Hello Math 4411 students, let's begin lesson 2, groups. This is a starting point of the group theory which will consume about 2/3 of the course. And that begins from the definition, of course, right here. A group is a non-empty set equipped with a well-defined binary operation that satisfies these three conditions. Number 1, associativity. Number 2, identity. And number 3, inverse. If you have these three, then you have a group. Now, some groups satisfy another condition on top of these three, the commutativity, or abelian condition. If a group satisfies all four properties, including this final commutativity condition, we call it a commutative group or an abelian group. However, I've never seen anybody calling it a commutative group anywhere in the world. Everybody calls it a abelian group, which was named after a German mathematician Abel, who worked on this and of course many other things as well. And out of respect on Abel, everybody is calling it a abelian group. I'll do the same, and actually so does our textbook author. The term commutative group appears only once, right here at the definition. Otherwise, it's a abelian group. So, if you have a group that satisfies all four properties here, it's called an abelian group. And if you have a group that satisfies only these three, but the last one fails, then it's called non-abelian. Let's look at some examples. First, some abelian examples. Let's begin with the set of all integers. And please note that it's a group under the addition, but not under the multiplication. Let's see. Associativity of the addition, yes. Identity is 0. Inverse is negative of that integer. And commutativity of addition, yes, 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 and yes. How about the multiplication? Well, we'll have associativity and commutativity, and identity 1, yes, but we don't have inverse in general. Say, for example, if you start from integer 2, then what's its multiplicative inverse? It's supposed to be 1/2, but that's not an integer. It's a rational number. You see, you go outside the boundary, so outside the main set, so that's not a group. So, if you want to consider multiplication, you'll have to go beyond the set of integers. So, what if I start from the set of rational numbers? Like this. The set of all positive rational numbers. Is that a group under the multiplication? Yes. And so is the set of all non-zero rational numbers. By the way, please remember these notations. Q plus for positive rationals, Qx for non-zero rationals. You can use some other characters too. Z plus Zx, R plus Rx, things like that. But if you consider entire Q, then you're going to fail because 0 has no inverse. And also, the identity property will fail for 0 as well. Okay, we went through some discrete and then one-dimensional example. How about some multi-dimensional example? Rn is a group under the vector addition, and M, so the set of all m by n matrices, m by n real matrices, forms a group too under the matrix addition. So like this, Rn, and each entry is a real number, and we can consider sum of each component. And then we can consider 0 vector, 0, 0, and so on. That's going to form the identity. And negative x, negative x2, x, etc. That's going to be the inverse, etc., etc. And you can establish the same thing essentially with respect to matrix addition as well. We have zero matrices and then negative matrices and things like those. Okay, so far so good, but all those examples were abelian examples. We did addition and multiplication basically. And as for n-dimensional cases, we only did addition, no multiplication. And if you do consider multiplication, now you're going to finally get out of this abelian boundary. Remember, matrix multiplication is not commutative. Remember that. I hope everybody went through linear algebra. So let's go. The set of all invertible, or in other words, non-singular, square matrices forms a group under the matrix multiplication. We call it the general linear group of degree n. The name is not that important for our purpose, but it's nice to know. But if you consider entire square matrices, all square matrices with real entries, then the answer is no. Here's a general definition of the general linear group. The set of all n by n matrices whose determinant is non-zero. So they're all invertible, they're all non-singular, they're all invertible. So we have this property here. Identity is okay, we have identity matrix. Inverse matrix is a problem, and that's why we needed this condition. Determinant is non-zero. Another example is special linear group. In this case, determinant is 1. For example, this is what the general linear group of degree 2 looks like. All the square matrices A, B, C, D, whose determinant AD minus BC is non-zero. In this case, I hope you guys remember the inverse matrix formula, 1 over AD minus BC times that matrix, and the determinants goes to denominator. So if it is 0, then everything breaks down. If it is non-zero, then this right-hand side expression makes perfect sense. And you can multiply this to the original matrix and then check if you have really the identity matrix in both sides. Check your computation. I'm going to leave the details to students because everybody is expected to have some linear algebra background already. If you go to the set of all square matrices of real entries, then the answer is no. You're going to get a matrix whose determinant is 0, kind of like this. You can rigorously prove it. Consider these two matrices, B and C, and neither is 0 matrix, but if you multiply, then you're going to get a 0 matrix. These kind of things are called zero divisors. And then you can prove that zero divisors cannot have inverse. If there were, multiply that inverse to either left-hand side or right-hand side, depending upon the location of your primary matrix. And then go ahead and algebraically prove that the other matrix is 0. And that's impossible because we started with non-zero matrices. So there goes a contradiction. Consequently, there's no inverse. You can rigorously prove it. The detail is left to the students. After all, I assume everybody went through linear algebra already. Okay, alright, we went through some natural examples. How about some artificial example? Here we go. Let's artificially define a certain algebraic operation, a binary operation like this, in the set of all positive rational numbers. And then let's see if this is a group under this operation. If yes, is it abelian? Wanna try? Stop the playback and then go ahead. So what do you have? Is it a group? Is it abelian? The answer is yes and yes. Yes, it's a group, and yes, it's an abelian group. So we'll have to check all these: associativity, identity, inverse, and also commutativity. So how do we check? Well, here's your associativity. And then we have to calculate the left-hand side and the right-hand side by brute force computation using this parenthesis first, and then see if you get the same answer. Go ahead. If you do it right, you're going to get the same answer like this and that. With fractions, so let's increase the font so that we can read better. See? They're the same. Okay, the detail is left to the students. Let's go back to the normal font. Now, identity. This is the operation. And then that has to be back to B. So what is your A? If you have 2, then 2B over 2. Looks like that's the identity. Is that true? Yes, you can check rigorously. 2 star A, A star 2. How about the inverse? So A times B has to be the identity 2 again. So from here, B is what? Flipping A over 2 to the other side, 4 over A. Looks like that's the inverse. Is that true? Check. Yes and yes. Maybe you're gonna need bigger font. Yes and yes. Okay, finally, commutativity. Well, that's going to be easy because all you have to do is to go through this, and this multiplication takes place in the numerator, and multiplication is commutative. So it's easy proof. There you go. A star B is AB over 2, and that's equal to BA over 2, so it's B star A. By the way, you don't have to follow this order. If you prove the commutativity first, then it's easier to prove identity and inverse. You don't have to do this twice. Just do it once and forget about this, and just this and forget about the other. You can do that if you establish the commutativity first. In group theory, it's not very important because we have only 3 things to check. But if you have a little bit more complicated algebraic structure, then doing this in strategical manner is going to be helpful. If you remember what we did for linear algebra, such as inner product and things like those, yes, we established a commutativity or symmetry first, and then that really helped us to do the other things. Okay, how about the next topic? We don't have enough time, so let's stop here. And we'll come back and discuss the unique lemma in the next video, and the cancellation laws too. Okay, maybe next video or maybe next 2 videos, depending on how quickly I go.